Hi, and welcome again to my Physics Online video lecture series. In today's video we're going to be talking about the Poynting vector. So we are continuing with our discussion of electromagnetic waves. So the Poynting vector, this is not a misspelling, by the way, it's named after somebody. The Poynting vector basically is a vector whose magnitude carries some information about the wave's intensity, and whose direction gives the propagation direction of the wave. So about this intensity bit, recall that intensity is given by I is equal to, or is defined by really, power per unit area, or in other words, amount of work delivered per unit area per unit time. So that gives you the intensity for a wave, and this is any wave in general. So this is waves in general. So we found this, or we defined this in our discussion of mechanical waves. So now we have our electromagnetic waves. And for electromagnetic waves, there's another thing that we might recall. That other thing that we would maybe recall is energy densities that go with capacitors and inductors. The energy density, lowercase u, is defined as the total energy, uppercase U, per unit volume. And for the capacitor is an E field, and so you have 1/2 epsilon naught E squared. For the inductor, in the B field, you have 1/2 of B squared over mu, or mu naught. So that gives you your energy density. Last but not least, we know that E over B is C naught. So these two things can combine to get us the energy density in terms of either only the electric field or only the magnetic field. So again, it should look like 1/2 epsilon naught E squared plus 1/2 mu naught B squared. But we can use E squared is equal to C squared, or C naught squared, B squared. And C naught in turn is 1/square root of mu naught epsilon naught. So if we come back up here, this E squared term that we said is C naught squared B naught squared, we could also call that essentially B squared divided by mu naught epsilon naught. And so if we substitute this for E, then what we end up getting with is that the energy density little u should look like 1/2 epsilon naught over mu naught epsilon naught. So that'd be 1/2 mu naught times B squared plus another 1/2 mu naught times B squared. And that's an instantaneous value. So add those two together, and what you end up with is B squared over mu naught. Likewise, we could use the fact that B squared is equal to E squared over C naught squared, which is mu naught epsilon naught E squared. And so if we substitute for B instead of for E, then we get little u is equal to 1/2 epsilon naught E squared plus 1/2, or 1/2 mu naught, times mu naught epsilon naught E squared. So cancel our mu naughts. You have a half, you have a half. That gives you a whole. You end up with epsilon naught E squared. So again, energy density little u defined as energy per unit volume, is either equal to any of these different forms. So we could say like 1/2 epsilon naught E squared plus 1/2 of B squared over mu naught. But we could also put it entirely in terms of the magnetic field B, or we could put it entirely in terms of the electric field E. So these are all valid ways of expressing that energy density. Now you may be wondering what energy density has to do with and how it's related to the Poynting vector and to intensity. Well, to get the answer to that question, we might consider what's happening with a wave that's carrying some energy. We know that the total energy that will be kind of like found within a wave must be equal to sort of like the spatial extent, let's say volume of that wave, times the sort of a density, energy density. Since little u is defined as big U over V, it follows that big U, the total energy, is little u, the energy density, times V. And so if I want to know how much energy is deposited by a wave in some amount of time, or how much work could be done by the wave, some version of that, I could say something like delta U is this energy density times delta V. And so now we ask, well, what is this delta V? Well, let's say that I have an electromagnetic wave, something like this, and then I've got my maybe magnetic field in and out of this page. Well, this thing, if I were to, maybe it's like a laser, I shine the laser on a wall, I end up getting a spot that's on the wall. Okay, the spot has cross-section area A. Well, the total sort of like volume that has passed through a given point as this wave passes through, that ends up looking like your cross-section area A times maybe like the distance delta x that this wave has traveled in that time. So delta V should look like A delta x. But we know that delta x, if this wave is moving at a constant speed, delta x is speed times time. So this ends up looking like A times C times delta t. Okay, so that is all this volume. Therefore, the energy deposited, delta U, which is lowercase u times volume, becomes U times A times C naught times delta t. And so it follows that little u times C naught is equal to big U divided by area times time. But that's just the same equation that we have over here. This right here could be rewritten as delta U over area delta time. The change in potential energy is the work done by the wave. So this means, in conclusion to this bit of a derivation, that little u times C naught is equal to the intensity of the wave. Okay, so wave intensity. Now basically just would say I is little u times C naught, but coming back here and looking at what a little u was defined as, that looks just like 1/2 epsilon naught E squared plus 1 over 2 mu naught B squared, or B squared over mu naught, or epsilon naught E squared, whichever those you want. All of these, there's another way of writing them, by the way. Instead of splitting everything up into just B or to just E, we could say that these are both E times B terms. So that means that I could come back over here and say that the intensity is equal to C naught, which again is 1 over square root epsilon naught times mu naught, that's my C naught term, times square root of epsilon naught over mu naught times E times B. So if we cancel some like terms and combine some other like terms, that means that my intensity is E times B over mu naught. That is also equal to, for what it's worth, therefore, E squared divided by mu naught C naught, or is also equal to B squared times C naught over mu naught. And this in turn gives me mu naught times 1 over mu naught epsilon naught. So this whole term could be rewritten as E squared times the square root of epsilon naught over mu naught, for what it's worth. Okay, the point being that we found what is the intensity of our wave. So now we have our Poynting vector. If we define the Poynting vector, usually with an S, to be given by 1 over mu naught times E cross B, what will that get for us? Well, the magnitude of this Poynting vector would then be E times B times sine of the angle between them, but E and B are always perpendicular to each other. E is perpendicular to B. So that means that my Poynting vector S, when it's defined this way, has as its magnitude 1 over mu naught EB. But that's just the same as the intensity that we found up here. So the magnitude of the Poynting vector is the intensity. The direction in turn is actually the direction of propagation of our electromagnetic wave. All right, so that's basically the power of this Poynting vector. Miscellaneous stuff that we can do with that. Well, we already know what our intensity is. We already know that the intensity, or the magnitude of S, would look like E times B over mu naught, or C naught epsilon naught E squared, etc. But this is kind of our instantaneous value. So maximum value, maximum intensity or peak intensity, should look like basically E max times B max over mu naught. Or in terms of the notation that we wrote it in the previous video, this would be E naught B naught over mu naught. We could also write it in terms of this right here. So you'd have C naught epsilon naught E naught squared. That's your maximum value. Recall that the E field and the B field are sinusoidal. So recall that E, the electric field value, is E naught times sine K wave times X minus or plus omega times T, and maybe some additional phase. Sinusoidal, like an AC signal. So it follows that our maximum intensity can be related to an average intensity by average is simply 1/2 of I naught. And from that we get stuff like our root mean squared values for E and for B, which I discussed in the previous video. So let's conclude with a quick example. Alright, so we've got this green laser pointer, basically like one that you might use, or that your teacher may use, professor, whoever, when lecturing to a largish classroom, like 40, 50 students. And if you were to look at the side of that laser pointer, one of the labels that goes on it says this is what wavelength and this is what power output to expect. Typical value for a green laser pointer for wavelength is 515, 520, or 532 nanometers. Typical power outputs, typically 1 or 5 milliwatts for this lecture style. Usually actually says less than about 1 or less than about 5, usually 5 for a lecture hall. Okay, and then you have a spot diameter of 1 centimeter. Usually it's roughly a circular spot. And so we want to know what's the average intensity, what's the peak intensity, and what's the peak E field magnitude. Assuming, of course, that we're looking at peak intensity means like maximum value in time, peak E field, maximum E field in time. We'll assume like a uniform distribution of the power through that spot, even though it actually is itself a function of space. It may not be a flat uniform distribution. In fact, one common distribution is the Gaussian distribution. We'll assume a flat distribution in space. Okay. Average intensity, to get that, your intensity value is equal to the amount of power per unit area. So we have 5.0 milliwatts divided by the area, which is here's the power, here's the diameter. Area is pi times r squared, which is pi times diameter squared divided by 4. So we'd have pi times 1.0 centimeters by 1 meter per 100 centimeters squared. This is times 1 watt per 1,000 milliwatts, but times 4. This times 4 is because I have an over 4 in the denominator, which is like a times 4 in the numerator. So plugging all of that into our calculator, what we get is about 63.6619. So let's call that 60, well, 2 sig figs would be 64. And then the unit is watts per square meter. Okay, what about the peak intensity? Well, this is basically an average intensity. We're taking an average power per area. The peak intensity would be I naught or I max or I peak. All those are equivalent for our purposes, and that should be 2 times the average value. So if you multiply by 2, you actually end up getting 127.3. So there's some rounding, So we could say 100, maybe we'll round it off to a whole number. We'll call it 127 watts per meter squared. If we really rounded it off to 2 sig figs, 130 watts per square meter. This would represent the maximum in time value of the intensity. So it fluctuates between 0 and this number in time. So the last part is, what about the peak E field magnitude? And to do that, I'm going to actually go ahead and kind of go to a new slide. So we're looking for the peak E field magnitude. That would be E naught, and that should be basically from I naught. And you get that because, again, your peak value of this would represent I naught, would represent, from our previous slide, E naught B naught over mu naught, but is also C naught epsilon naught E naught squared. Okay, so this would be C naught epsilon naught E naught squared. And so I can rearrange the equation to get that E naught is the square root of I, or I naught, divided by C naught epsilon naught. So E naught will be the square root of, we had 126 point whatever watts per meter squared, divided by C naught. Well, this whole square root of C naught epsilon naught thing, this itself is square root of, or 1 over square root of mu naught epsilon naught. And so my sort of epsilon naughts can cancel here. And so this ends up having a mu naught term. How do you want to plug it into your calculator kind of is up to you. I guess since I've written it this way, I will write it down here in this way. And so this is roughly 3 times 10 to the 8 meters per second for C naught, and 8.854 times 10 to the minus 12 farad per meter for epsilon naught. So that one we got to throw into a calculator. But when we put it into the calculator, we get a value of about 218.9. So let's call that 220 volts per meter. All right, so that is a 3-parter example for everybody of finding the electric field. I think that suffices for today's video. Hopefully you've learned something about the Poynting vector, and thanks for watching.